A multiverse of evolving universes solves a crucial philosophical problem. Why is ours so finely tuned for life? Fine-tuning is defined as the observation that out of the set of all possible physics, the subset that allows the formation of intelligent life is very small. Planet Earth is fine-tuned, for example, to allow for our species to evolve. The reason why is because it is one out of billions of trillions of planets in the universe. There is hence no mystery in why it exists. It is simple probability. Yet at one time, a mere 450 years ago, the human race had no knowledge of worlds outside the solar system and believed that the planets and stars they could see were not worlds of their own at all. They believed instead that Earth was uniquely seated at the center of the universe. While some humans imagined other worlds, no evidence for them existed. In fact, what evidence there was against it. The lack of stellar parallax, the motion of the fixed stars with the seasons, was an argument against even basic heliocentrism, the first step to accepting that the sun is the mother of the Earth. No one believed that the stars could be so far away that we could not see them move unaided. Another piece of evidence was that they believed, if the Earth moves, we should feel it moving. Aristotle had told us so, but Galileo had observed otherwise when considering ships moving out at sea. He observed that those on the ships could, on a calm enough day, not feel the ship move, but the supposedly stationary people on the shore appeared to be moving. This is called Galilean relativity. Those who promoted the idea were mocked, or worse, handed to religious authorities for correction, and if they did not recant, punishment up to and including burning at the stake. Only when Galileo turned his telescope to the moons of Jupiter did human beings begin to collect the proof that there might be other worlds, ones that didn't orbit the Earth. Yet it would take centuries for us to determine that other stars have planets and resolve the fine-tuning question. The vast majority of planets are not fit for life as we know it. We are at the beginning of a new era now, with the launch of the JWST and sensitive instruments for detecting gravitational waves such as LIGO, where we can probe deeper into space and time than ever before. There is no telling what we will discover and no reason to suppose that our universe is the only one, the center of everything. In fact, a basic principle of science is that we are not in a special position in the cosmos. Yet our relationship to the Big Bang, the origin of time, is a kind of specialized position if we consider it as the true beginning from nothing. If, however, the Big Bang is not the beginning of all time, but only the beginning of time for us, then is that not more in keeping with that principle? Until our instruments can peer into such questions, we can try to answer them using probability, asking, if there is a multiverse to explain our universe, what form should it take? Fine-tuning arguments for the universe go back to cosmologist Brandon Carter and his 1974 paper based on a lecture celebrating the 500th birthday of Copernicus. In this lecture, Carter argued that the universe had to be finely tuned in a myriad of ways, such as the value of the fine structure constant at 1 by 137, for it to have developed intelligent life. Life requires a universe that can form stable matter and can clump together to form stars and planets. It also has to allow for a variety of stable elements as building blocks for life. We know of no physical process that guarantees this be so. See the table below for all the physical constants that life requires. The strong force that keeps atomic nuclei together, the weak force allowing unstable nuclei to decay to stable ones, electromagnetism to bond atoms into molecules, and gravity to clump it all together, all depend on finely tuned constants and relationships that, should they be changed, would not allow matter to exist, let alone life. Given that our universe is incredibly unlikely, we can come up with two reasons why it exists. Many universes exist, all with different laws of physics. These universes are produced by a physical process that scans through the possibilities. Eventually, some are produced that allow for intelligent life. They are the only observable ones. A creator. Being with perfect foresight creates a universe with all the right characteristics for intelligent life. These are, of course, not mutually exclusive. A creator being could exist, but work through secondary processes such as evolution to create. Our universe supports intelligent life because we are here to observe it. This is called the Anthropic Principle. It is an example of selection bias. We bias the universe by only being able to exist in one that allows us to exist. Anthropic Principle aside, arguments for and against fine-tuning decidedly tip towards being for it. But when it comes to the details, there are a few fallacies to avoid. The cheap binoculars fallacy. This one goes, don't spend money on binoculars, just stand closer. This fallacy means that we can't only consider universes that are in the neighborhood of our life supporting one. By zooming in on such a neighborhood, we can make arguments that don't make sense for the wider view. For example, the electron mass to down-up quark mass is precisely in the region that allows for the production of hydrogen, which gave birth to the first stars. If it were much higher or lower, the universe would have been made of all protons or neutrons and no molecules could have formed. We can't assume there is any reason for it to be what it is now other than chance or some other physical process. The flippant funambulist fallacy. This fallacy goes, tightrope walking is easy. Just walk in all the places that you can stand and not fall. This means that the path the universe must take through parameter space and still produce life is carefully balanced. Even if you can change one parameter a lot, others are carefully constrained, like walking a tightrope. It is still fine-tuned. The sequential juggler fallacy. This fallacy says, juggling 5 balls is easy. Just throw and catch them one at a time. That isn't really juggling. The universe has to satisfy several constraints simultaneously, not only one or another. This makes it vastly less probable. The evolution of our universe. Now, either we suppose that for some reason, 1, the laws of nature cannot be different than they are, which seems far-fetched but possible. 2, a virtually infinite number of random universes actually exist. Or 3, the universe evolves in such a way as to make the possibility of life far more favorable. Mind you, this doesn't mean the universe is necessarily trying to produce life. It is purely anti-teleological, without purpose. Rather, it is simply a survivor in a long line of universes that gave birth to it. In order for the universe to be part of an evolutionary cycle, it needs 3 things. A means of encoding that it can pass on to the next generation, a means of reproduction, a means of variation. The encoding likely is part of the initial conditions of the universe, as DNA are our initial conditions along with some raw materials. Hence, the mother universe that produces this one must form black holes, the means of reproduction, in a particular way that confers its properties onto the daughter's Big Bang. These properties ensure that the daughter can, likewise, produce offspring universes and also pass along its properties via initial conditions. These are the laws of physics and physical constants. These initial conditions, however, must experience some amount of randomness. Otherwise, there would be no way for the laws of physics to vary and allow new traits to emerge. Quantum processes could provide such randomness. We know, after all, that physical constants vary in quantum field theory at different energy levels. It is possible that variations in low-energy physical constants could arise from variations in the extreme energies of the Big Bang. We don't know if this mechanism is true, however, and the chances of observing it are slim. It is possible that, like quarks, we can infer its existence from measurements of other properties. But for this analogy to make sense, we would need more than Bayesian arguments. The quark is, after all, an essential ingredient in our standard model of matter. That we cannot view quarks directly doesn't mean that we can't measure them indirectly to great accuracy. One way of testing if a multiverse exists is using the principle of mediocrity. Boltzmann, 1895, came up with this principle, and it goes like this. Given the second law of thermodynamics, everything runs towards thermal equilibrium. Why then is our universe so far from equilibrium? Well, says Boltzmann, perhaps random statistical fluctuations produce regions of low entropy that are far from equilibrium. We know from fluctuation theorems that this is possible. Since life needs low entropy, it only forms in those statistical fluctuations. This brilliant idea has a fatal flaw, actually a few, because it suggests that life is a mere fluctuation, a statistical aberration, and that, therefore, the universe should only contain the bare minimum of low entropy to allow it to exist. In fact, the minimal entropy requirement would be for intelligent life to blip in and out of existence with false memories imprinted. These are called Boltzmann brains. We are not Boltzmann brains. We find ourselves living in a universe billions of years old with billions of parsecs of low entropy, far more than we could possibly require. If you apply the principle of mediocrity to the Earth versus other planets, you do in fact find it to be true. The Earth is a small life-giving planet floating within vast reaches of uninhabitable space and deadly, lifeless worlds. This is what we would expect to see if our evolving on Earth was a statistical aberration. We can go even further, however, because we appear on the Earth not only in space, but in time as well. How likely, we can ask, is it that we should appear on a 4.5 billion-year-old Earth versus a 1 billion or a 1 trillion-year-old Earth? That is easy enough to answer. Because of the Sun, Earth is only habitable for a fixed length of time, about 5-6 billion years. Life appeared on Earth about 3.7 billion years ago, and the Earth should remain habitable for 1 to 1.5 billion years. This means that humans are appearing on the Earth late in its habitable stage. This seems less likely versus appearing 2 billion years earlier until we look at how life on Earth evolved. While life did appear on Earth 3.7 billion years ago, it did not develop sexual reproduction, which accelerated evolution significantly, and multicellular life until about 1 to 1.5 billion years ago. All life before then was single-celled. Hence, we have evolved about halfway through the Earth's multicellular life period, as we would expect. If Earth is typical of intelligent life-producing worlds, then choosing such a one at random, we would in fact expect to come into being late in the life-bearing stage when it had reached sufficient complexity for intelligence, but somewhere perhaps in the middle of its multicellular phase. Now, just by looking at it, we can't say if the universe escapes the principle of mediocrity any more than we can say that about the Earth without observing other worlds. Thus, until we have evidence, we can only apply it to models of multiverses. Any multiverse proposal, however, should escape the principle of mediocrity. It cannot rely on random fluctuations to be taken seriously. Eternal inflation is one example of a multiverse proposal that can suffer from problems of mediocrity. In this theory, universes are constantly generating, inflating, then stopping their inflation. If you look at all the universes at a particular time, there are vastly more universes that are hot, young, and inflating than ones that are cool, old, and not, like ours. That means that intelligent life should observe their universe to be far hotter and younger than ours. In fact, a universe as old and cold as ours would be 1 to 10 to the power 10 to the power 56 likely to be observed, an incredibly small number. This is called the coolness problem. Unfortunately, in an infinite multiverse with infinite universes, it is impossible to say what is or is not likely without some kind of measure over the universes. A measure is exactly that, a way of determining the size of some infinite or uncountable quantity. This is called the measure problem. Eternal inflation has to provide some kind of measure. The likelihood of our universe would depend entirely on that measure and be sensitive to that choice. This is a general problem with fine-tuning and inflation, so we can't say if it survives the mediocrity test or not, which is a bad thing. Evolutionary universes, however, avoids the mediocrity problem. First, universes have to last long enough to produce a significant number of black holes, so they have to have some longevity. We know that the first stellar collapse, black holes likely formed after the universe was about 1 billion years old. The growth of these supermassive black holes is linked to the growth of galaxies. Thus, a universe that forms galaxies is also likely to form black holes. Still, 1 billion years is considerably younger than the age of the universe now. Shouldn't we expect the universe to be much younger than it is, and therefore aren't we suffering from mediocrity again? Not really. The difference between black hole-based reproduction and eternal inflation is that new universes are produced by altering a spatial direction into time by the space-time warping properties of black holes. The direction pointing at the center of a black hole in our universe becomes the time dimension for the daughter universe. Therefore, if you were to take a survey of all the universes in the multiverse, you could not choose a particular time at which to survey them. They all keep their own times. This means there is never a typical age for a universe according to some global multiverse clock, so it escapes that problem. The better way to apply mediocrity instead is to ask whether our universe is compatible with a universe that reproduces via black holes using what we know about evolution. That is, does the universe live long enough to reproduce as much as possible? We would expect to live in a universe that produces a lot of black holes, and ours does. By the Anthropic Principle, we would also expect that black hole formation depends on similar processes as the formation of stars, planets, and galaxies needed for life. And it does. Moreover, we would expect to live in a universe that produces as many black holes as possible. And we do. We live in a universe where nothing can escape them. At some point in the far distant future, all matter in the universe will have fallen into a black hole. You might ask where all the matter comes from? Was it created with the very first universe somehow? The answer is that matter comes from inflation, which is also a property of black hole to Big Bang universe creation. As long as space-time is inflating faster than light, which occurs during the very initial stage, you can, according to inflationary theory, create matter and energy from nothing. And the vast majority of matter in a new universe would come from this and not from the mother universe, which imparts only a seed. Thus, our universe appears to be the kind of universe we would expect to live in, provided that it reproduces from black hole production. What about coolness? Wouldn't a very hot, dense universe be far better served for black hole production? Actually, no. A hot, dense universe tends to have very average density, which is below what is needed to form black holes. Indeed, for years, it was a mystery that black holes formed in this period at all, rather than later when more supermassive stars formed. Yet we have evidence from quasars that they did indeed form. These early black holes, in simulations, formed from cold gas streams that collided and created super-dense pockets that immediately collapsed into stars and black holes without going through all the stages of formation that we see with later black holes. It seems as if the universe is finely tuned for black holes, but what about us? We have to be careful to avoid the flippant funambulist fallacy. While the universe could be finely tuned to produce black holes, that doesn't explain why it produces molecules. Black holes only require one thing: matter. The Anthropic Principle explains why our universe needs molecules, but we find that the black hole principle saves us in other cases where the AP fails. Is the universe too big for us? Roger Penrose has argued against the multiverse based on the Anthropic Principle because the universe is too large. Sentient life doesn't need all this room. This is the problem that kills many multiverse proposals with mediocrity. If the universe reproduces via black holes, it exists in order to make black holes and not sentient life at all. Then you would expect the universe to be very large indeed, because the bigger it is, the more black holes it can make. We know how big the observable universe is, about 95 billion light-years across. Ideally, the most production would occur in a universe that is infinitely large, but even so, we would not be able to see any further than light could reach us. All we have to work with is the observable universe. The size of the observable universe is determined purely by the amount of time that has passed since the Big Bang and the expansion rate over that time. Thus, it has little to do with the total size of the universe. The biggest advantage of the Big Bang from black hole theory is that it gets us away from the Anthropic Principle as the guiding rule for our universe's existence. Unlike the Earth, the universe doesn't seem to be just right for life. It does, however, seem just right for stars. And where there are stars, there are black holes, and where there are black holes, there may be other universes. Thank you so much for watching.